Okay, so I'm going to show you how to prep a molecule with this with the new version of OSPREY that comes with the graphical user interface. So we'll give you a distributable that you can run on your computer. This program runs on Linux, Ubuntu specifically, Mac OS Catalina, and Windows. At least it should run on all three platforms. And it runs on other Linux variants if you compile it and run it from source. So let us know what operating system you'd prefer to use, and we'll try to make sure that this works with that operating system and get you the executable. Okay, so the first thing you're going to do is import a PDB. Sometimes the open window opens behind the main window, so just look out for that. I grabbed the Armadillo Repeat Protein directly from the PDB 6S88 to show you how you might do it from scratch. And all you see here is an atom cloud. And so what I'm going to do next then is I'm going to run through this prepare menu and basically do each of these 5 steps to prepare it, and then this is sort of equivalent to what OSPREY GUI did for you in the past, with the exception, the OSPREY prep did for you in the past, with the exception of generating templates. So first, you're going to filter out any atoms that you don't want. So we don't want this EDO. By default, water is filtered out, so we'll leave that filtered out. And we want chain A, which is the protein, and then chain B, which is the peptide, to stay in there. So there's no save button. You can just exit out and the state is saved. Now let's see the missing atoms. If we need to add any missing atoms, we'll automatically add these missing atoms. And we found that, yes, there is one OXT needed, oxygen there. So we'll just leave those as the default 2 with the atom added. And then what the GUI does is you're going to want to specify your bonds. So the first step is to just click Add Bonds Automatically. So you add these bonds automatically. Now, if you wanted to come in and modify some of your bonds because you think like it got something wrong, you could identify what you think it got wrong, maybe by eye or because you did this before and you know it got something wrong. You click on it and then the particular bond of interest, and then you can modify which atoms an atom is connected to, right? So if I can remove this bond, as you see here, and it removes the bond to the alpha carbon. But I'm going to leave it as the default now. Now I need to add hydrogens. So I'm going to first see clear all hydrogens. There are none, so that's good. And then we'll just add all hydrogens automatically. And say that actually the orientation of these hydrogens here is incorrect. Let's actually look at this one here. What we could do then is we could change its hybridization, right? But I'm going to leave everything as its default. And the next thing you want to do is you're going to want to minimize your structure. And so I do typically run it for like 100 steps. Since we're doing a demo here, I'm going to reduce that so it runs quicker. And we'll reduce both the protein and the peptide. Okay. So the minimization has completed, and you can toggle in between the minimized and the unminimized versions just to see how your molecules change. We'll leave everything minimized. And now what you're going to want to do is export or save this as an OSPREY molecule, a prepped OSPREY molecule. So I'm going to create a new folder here called demo fluorine. Okay, and we'll call this as the arm complex reps. All right. Now we can close the preparation window, and we're going to create a new conformation space. Now, the first thing you do is you're going to open back up your OSPREY molecule. Okay. And so here we have it. This is what we were just looking at. And now what we're going to do is specify the flexibility and the mutability of the system. So in our case, what we're going to do is we're going to say, I believe it's arginine 6, we're going to let it mutate to alanine. And this is in the peptide. We're going to say lysine 5 is flexible. And we'll say, I believe it's serine 371 in the protein, we'll say it's flexible. And what is it? Some molecule, residue of 407 will also be flexible. Okay. So that's our plan. So the first thing we're going to do is call this, give this a conformation space a name, call it arm complex comp space. Okay. And we're going to add now mutations. So the peptide is chain B, and we said we wanted arginine 6. We're going to let it mutate to alanine. And if you first open up the mutations window, you'll see that there are no mutations available to you. So what you need to do is add a rotamer library. So click the add button and then click the level rotamer library. And this gives you mutations you can now use. And this is where you would add your you would create a conformation library with your phosphorylated tyrosines, for example, that would allow you to use these phosphorylated tyrosines in different places. And that would show up here, and you just would add that from a file. Okay, so now we've specified our single mutation from arginine to alanine, and we don't have any in chain A. That's as we want. And so we did say we had 2 flexible residues in chain A, 371 and 407. So I'm going to make serine 371 flexible and choose 19 out of 19 of the conformations. Good. And we'll leave the discrete and continuous settings as default. And then we'll add a new one, just for residue 407, glutamate. And we'll leave the discrete and continuous settings the same as well. And so if we look here, we now see that there are a total of 171 conformations just with these 2 flexible residues, but the combined conformations of the entire structure is 171 now, because we haven't yet specified anything on chain chain B. So here, one thing to note is that the arginine, even though it is mutable to alanine, we haven't yet specified that arginine itself can be flexible too. So let's change that by clicking the edit button. And we'll say add all of the arginine and alanine conformations by clicking the select all, and we'll leave it as a continuous. We'll leave continuous with the defaults. Okay. And now we also said we wanted lysine 5 to be flexible, so I'm going to go ahead and choose that to be flexible. And now we see we have a total of 1,008 conformations in the peptide. So combined with chain A and chain B, multiplied together is 172,000 and change. Okay. So now we've defined our flexibility and mutability, we need to compile our conformation space. This step can take a minute. So I'm going to go ahead and click the compile button. And you'll see that there are progress bars here, but they don't, it can take like 5 or 10 minutes depending on the size of your system that you're working on. And so I'm going to pause the video and come back later. Okay, so the confirmation space compiled successfully. We see here. This just for reference, this took about, let's say, 10 to 15 minutes on my computer. I didn't note the time that the videos that I paused the recording just a few minutes ago, but you could do the exact calculation if you want to by looking at the times. So what the next step is to do is to save the confirmation space. So I am going to save it, and we are going to compress it. So we'll leave the settings as default, and we'll hit the save button. Pops up the window behind the current window. It says where you want to save it. So we'll call this complex conf space. That's CCSX. Okay. CCSX is compiled comp space compressed. Okay. Now I am going to hit, it's saving that. It can take a couple seconds to save it. There's no progress indicator, but if the screen seems a little slow at this point, that's why. I then hit the finish button. And what I'm going to do now is I'm going to split the confirmation space. Because now, if you recall with K-star, we have the complex, and then we have the apoprotein, and we also have the apoligand. So by splitting the confirmation space, we're going to create these confirmation spaces for the unbound protein. So chain A is the protein. So we'll call this the ARM protein comp space, and then save that. And to save chain B as ARM ligand. Okay. And now we are going to close, well, just for good measure, I'm going to actually save my confirmation space with the complex as well, with all of the flexibility and mutability parameters for later, so I can look those up, reopen it, and modify them if I want to. So I'm now going to close this and open the confirmation space for the ligand. We'll start there. Now it's already prepped. It's already, the flexibility and mutability are already chosen. As you can see, these are just copied directly from the complex. And so we have to compile it. As you can see, this goes much quicker than the complex because it's fewer atoms and fewer force field parameters to calculate. We are now going to save it as ligand comp space.ccSX. I already had one there with that name. And now lastly, we're going to compile the apoprotein comp space, again from the split complex. Okay, and just to confirm, we have residues 371 and 407 are flexible. And so it looks good. We can compile it. Now this is probably going to take a while too, just because there are many more atoms. So I'm going to pause the recording and come back to it when it's done. Okay, so the apoprotein confirmation space compiled successfully. I'm going to save that one. So now if we look what I have in this directory, I have my sort of comp space definitions here, and then the complex prepped OSPREY molecule is just the first thing that we did. And then most importantly, I have these 3 compiled conformation spaces that are compressed with the X. So the protein, ligand, and complex. So now what you want to do is you want to run these in OSPREY, load them in OSPREY using Python as we do with our other designs. So I'm going to go ahead and for right now, I'm going to go to the OSPREY 3 repository. We typically you would typically want to get the examples directly from the version of OSPREY that is installed on your computer because the examples change each version. But I am going to just pull this right from the repository because I know I'm running the latest version of OSPREY. And I'm going to look at this kstar.py script, and I'm going to get it, download it. Let me get the script directly from here. And what were the names of those compiled comp spaces? The complex comp space, ligand comp space, and protein comp space. All right. So right at the beginning of the file, we're going to load them. Okay. And let's see. K-star, we're going to put in the protein, ligand, and the complex. Now, where are those used anywhere else? Let me see. All right. And I believe that's all we need to do. So let me see. We now use Python and we can just run the kstar.py example. And so this is going to take some time. So I'm going to go ahead and pause it, and I will come back when it is complete. Okay, so the kstar program ran to completion. And what we see is that the mutation of arginine at position 6, given our flexibility parameters to alanine, is bad for binding by about 9 orders of magnitude. If we look at the lower bound on the K-star score and the upper bound on the K-star score for arginine, 111 to 112, versus the lower bound on the alanine of 102 and the upper bound about 102 as well. So I hope this has been helpful. If there are any questions, or if you run into any issues, let us know.